Okay, great. And so our next speaker is Shande Houlihan, and his thesis is a computational framework for emotion understanding.
We spend a lot of time trying to figure out what other people are feeling. And there's a long history of approaching this as a problem of perceptual decoding. The idea being that our expressions have been evolutionarily and culturally honed to convey signals that observers can reliably decode. And this seems reasonable. It would be adaptive to detect signals of aggression and affiliation from conspecifics. Congenitally blind babies have innate smile responses, and certain facial conformations evoke rapid, maybe even automatic neurobiological processes. But there's also a long history of people pointing out that the interpretation of expressions depends heavily on context. For instance, manipulating contextual cues about what event someone is reacting to can cause large categorical shifts in how even canonical expressions are interpreted. This long-running debate has mostly revolved around whether, when, and to what degree the interpretation of expressions depend on context. What's received relatively little attention is how people actually reason about contextual information. One cause for this is that modeling context is hard. But I think that the theoretical, methodological, technical developments of the last decade are making this endeavor tractable in new ways. So over the next couple minutes, I'll highlight how we've been building on these developments to model human emotion understanding. In the first part of the talk, I'm going to completely set aside expressions and focus on how people use contextual information about situations, like what someone did and what events occurred, to reason about emotions. And then I'll circle back to expressions and show how building formal models of context sets you up to make new progress on old problems. People have rich mental models of emotions, and this is especially evident when we have to anticipate others' reactions. To illustrate, think about what emotions you expect the person pictured here to experience in these various situations. She is a contestant on a popular game show that implements a high-stake public one-shot prisoner's dilemma. If she and the other player both cooperate, they split the $12,000 jackpot. In this case, people predict that she'll feel joyful because she got what she wanted, and relieved because if her opponent had defected, she would have won nothing, in which case people predict that she'll feel disappointed because she got less than she hoped, embarrassed that she was so publicly taken for a sucker, and jealous that the other player won the entire $12,000. Whereas if she was the one to steal the pot, people predict that she'd be embarrassed for a different reason, this time because she was publicly dishonest and selfish to another's detriment, etc. So how do observers translate sparse information about these events into such rich representations of her emotions? It's not like people have an innate association between cells of a payoff matrix and emotions. So to build a model that computationally recapitulates human emotion prediction in this domain, we need to formalize how observers reason about what events mean to the players. And in this endeavor, we took inspiration from a breadth of prior work, much of it from people in attendance here, including multiple Glushko and Rommelhart recipients. Two components that I'll briefly highlight are that we adapted appraisal theory, which is the idea that emotions reflect someone's subjective evaluation of events with respect to their beliefs and preferences. So for instance, did I get more of something I wanted than I expected to? Could I have gotten more if I had acted differently? And integrated this with inverse planning as a way to infer beliefs and preferences from sparse observations of intentional actions. And all of this is situated in an intuitive theory of emotion, which reflects people's mental model of other minds. So here are the average empirical predictions of joy that I was showing previously. And when they're stacked like this, it's immediately obvious how intensely social people's concept of joy is. Observers expect players to feel more joy when they split the pot cooperatively, shown in green, than when players win twice as much money acting deceptively, shown in red. And now I'll show the expected values of the model's predictions of joy on the x-axis. In this case, the model is a good match for people's predictions. We can expand this from joy to 20 nuanced emotions, from a $12,000 jackpot to pot sizes that span 4 orders of magnitude, and to a variety of different contestants on this game show. And it seems like this model is able to capture people's predictions of players' emotions with some success. But importantly, the model is not just learning a mapping between events and emotions. It's reasoning, like we think the observers reason, about what the situations mean to players. And this information is represented as a distribution over appraisal variables computed by the model. This space includes abstract representations of subjective utilities, prediction errors, and counterfactuals over social values and beliefs. And a key idea here is that computed appraisals act as a latent mental grammar of emotion understanding. So by formally assuming that human emotion predictions reflect a lossy compression of computed appraisals, we're able to learn functions that express emotions in terms of computed appraisals generated by the model. For example, the model learns that envy is a function of how averse someone is to getting less than his social partner, which makes intuitive sense. And here I'm showing 2 players who are inferred to have different preferences. Since the software engineer is inferred to be more averse to getting less than others, he has a higher preference, the model predicts that he will experience more envy when his opponent steals the whole pot, compared to the city council member. And this parallels with how humans translate inferred preferences into predictions of envy, which is evidence that the model has successfully reverse engineered something about the structure of human emotion concepts. So let's now return to expressions. Now that we've formalized how observers reason about event context, we can combine this model with off-the-shelf computer vision models to integrate expression information. The key idea here is that expressions are treated as data to be explained in terms of a theory of mind. So here's an example of an expression that a player on this game show actually made. With $36,000 at stake, think about which of these 4 events you think she's reacting to. Raise your hand if you think that she cooperated with her social partner and split the pot between them. Raise your hand if you think that she tried to cooperate but was duped and her trading partner stole the entire jackpot. Raise your hand if you think that she stole the entire jackpot, leaving her partner with nothing. And raise your hand if you think that they both defected and both left with nothing. So the model is going to generate emotion predictions from the event context for each of these 4 possible events, and then reason about which of those predicted distributions is likely to have generated the observed expressions. And by calculating the likelihood of the expressions under each of those predicted distributions, is going to adjudicate between the alternative event hypotheses. And so, like you, most people said that they thought that she cooperated and split the pot with her partner. Some people thought that she stole the entire pot, and very few people thought that she won nothing, either by being taken for a sucker or trying to steal the pot and not being successful. But in this case, that's exactly wrong. She actually tried to defect, her opponents actually defected, and they both got nothing. This was her actual reaction to that event, right? And we're all wrong about this. And importantly, the model is wrong too, right? But it's wrong in exactly the same way that people are wrong. And this isn't a cherry-picked stimulus. What I'm showing here are the judgments that people made for all of the players, 24 players, who participated in DD games, and the correct judgment is on the right. my laser doesn't make it that far, but is on the right, is the unhatched bar. And then people's incorrect judgments are the other ones. And you can see that people are systematically biased against the correct judgment in this case, and that the model closely matches that pattern of behavior. And this is true across all of the expressions that we have. People aren't always systematically biased against the true response, but regardless of whether they are correct or not, the model matches their judgments quite accurately. And so that's an interesting thing about this work, and this approach more broadly, is that a lot of the ways that we build these models feels quite obvious. We're comparing expressions to our predictions and then adjudicating between hypotheses, and that raises the question of why this hasn't been built before. And one reason is definitely that we have new tools, but the more important thing, in my opinion, is that this modeling approach invites thinking about cognition in productive ways. And investing the work in building causal generative models of cognition seems to be an effective way of reverse engineering social cognition, offering insight into the human mind, and in this case, providing a formal account of behavioral patterns of emotion understanding that no existent theory can explain. So I've had the great pleasure of working with some of the most brilliant and kind people I've met, and in particular, Rebecca Sachs had a pivotal role in this work. She was involved in detail in every step. And thank you to all of the participants and mentors and collaborators.